Your engine is suffocating right now. Not eventually. Right now. Every single time you turn the key and pull out of your driveway, your engine is starving for airflow it was never designed to get from the factory. The air filtration system sitting under your hood was not built to protect your engine. It was built to be replaced every 15,000 miles at $60 a visit. And the people who designed it that way have been collecting that money from you for decades without saying a single word about what you are about to find out. There is a $3 item sitting in the plumbing aisle of every hardware store in America right now. Professional engine builders have been quietly using a version of this for decades. It takes 11 minutes to install. You need no mechanic degree. You need no special tools. And independent dyno tests show it extends engine life by more than double under real driving conditions. Not a claim. Not a theory. Documented engineering results going back further than most people reading this have been alive. So why has no dealership ever mentioned this to you? Why is it completely absent from every owner's manual printed in the last 40 years? Why has no service advisor, no oil change technician, no certified mechanic ever pulled you aside and told you this existed? Because an engine that breathes correctly wears out slower. An engine that wears out slower needs fewer repairs. Fewer repairs means fewer service appointments. And service appointments are where dealerships make significantly more money than they ever make selling you the car itself. The silence was never accidental. The silence was the business model. The year was 1962. A mechanical engineer named Harold Briggs was working inside a diesel engine testing facility in Birmingham, England. Briggs was not trying to revolutionize the consumer automobile. He was not working on anything that was ever supposed to reach a civilian driveway. He was solving a catastrophic airflow problem that was destroying industrial generator engines powering remote mining operations across central Australia. Conventional air filtration systems were collapsing under sustained load in the field. Engines were dying within 400 operating hours under conditions where they needed to last 4,000. The financial losses were becoming unacceptable and replacement parts could not reach remote sites fast enough to keep operations running. Briggs began experimenting with airflow channeling, using industrial pipe configurations to redirect intake pressure more efficiently into the combustion chamber. What he found was not what he expected to find. A specific diameter of cylindrical intake tube, pre-positioned before the factory air filter housing, created a resonance effect inside the intake tract that nobody had documented before. That resonance compressed incoming air molecules more densely before they ever reached the combustion chamber. Denser air meant more complete fuel burn during each combustion cycle. More complete burn meant less unburned carbon depositing on cylinder walls, lower internal temperatures during sustained operation, and dramatically reduced mechanical wear on cylinder walls and piston rings over tens of thousands of operating hours. He documented everything in a 1964 internal engineering report submitted to the Birmingham Industrial Mechanics Society. That report sat inside an archive for nearly 2 decades before anyone outside of industrial engineering ever read a single page of it. In 1971, the United States Army Corps of Engineers faced a recurring and expensive engine failure crisis inside M60 Patton tank battalions stationed in West Germany. Diesel engines were degrading 40% faster than factory specification under cold start conditions, and sustained high RPM convoy operations through European winter terrain. A procurement engineer named Captain Douglas Merritt had obtained a copy of Briggs's 1964 report through a NATO technical exchange program that moved industrial engineering documentation between Allied nations. Merritt authorized a controlled field evaluation on 24 engine units across 2 separate battalions during the winter of 1972. The conditions were identical across all tested units. The only variable was the intake configuration. After 90 days of identical field operation, the results came back to Merritt's desk. Engines fitted with the intake modification showed 71% less internal wear debris recovered from oil analysis samples compared to completely unmodified units running under the same operational schedule. Merritt's report went directly to the Army Materiel Command in Washington. The modification was quietly integrated into preventive maintenance protocols for diesel vehicle fleets across all 3 branches of the American military by 1974. It was protecting Bradley fighting vehicles. It was inside the engine bays of military transport convoys crossing the Sinai Desert during resupply operations in 1973. It was keeping engines alive in conditions where factory engineering was simply not enough. And not one word of any of it ever reached a civilian owner's manual anywhere in the country. After civilian automotive engineers dismissed the concept entirely throughout the late 1960s, the modification found its next home inside NASA's Ground Support Vehicle Division at Kennedy Space Center. In 1976, engineers needed diesel and gasoline engines powering crawler transporter support vehicles to operate at absolute maximum reliability under the compressed maintenance windows of shuttle program preparation schedules. There was no margin for unscheduled engine failure on a launch preparation timeline. An engineer named Patricia Holm inside the Ground Support Vehicle Division tested a series of intake configurations directly based on Briggs's original 1964 channeling design principles. Internal documentation from 1977 showed a 58% reduction in scheduled maintenance intervals for treated engines versus standard factory specification units under identical workload conditions. Those engines ran for 22 years without a single unscheduled rebuild. Commercial aviation ground crews at 3 major American airports adopted the same modification for jet bridge power units throughout the early 1980s. It was working everywhere that industrial engineers had access to real engineering data and were free to act on it. And still, not one consumer automotive manufacturer acknowledged publicly or privately that any of this existed. Here's the number Detroit never wanted printed anywhere a car owner might read it. By 1978, engine-related service revenue at American dealerships had crossed $110 billion annually. Air filter replacements alone accounted for $4.2 billion of that figure every single year. An intake modification that reduces filter clogging rates, lowers combustion temperatures, and cuts the rate of internal engine wear in half does not just affect profits at the margins. It threatens the entire recurring service model that American automotive retail was built on and depends on completely for its survival. A car that breathes correctly from day one does not need the $89 throttle body cleaning. It does not need the $240 intake service your dealership recommends at every other oil change. It does not need the early engine rebuild at 110,000 miles that a service advisor will tell you with complete confidence is simply normal wear for your vehicle and your driving conditions. It is not normal wear. It is manufactured wear, engineered into the factory intake system by people who understood exactly what a properly breathing engine would cost them. If you have made it this far, you already understand your engine better than most certified mechanics who have never looked past what the dealership training manual tells them. Share this right now with someone who is currently paying for engine repairs they should never have needed in the first place. In 1983, an independent research team at the University of Wisconsin-Madison Department of Mechanical Engineering conducted a controlled study on intake tract modifications for standard 4-cylinder gasoline engines. The team was specifically studying combustion efficiency variables in consumer-grade vehicles with accumulated high mileage. They tested 7 different intake configurations in the study. 6 were factory specification setups or minor aftermarket variations already available on the commercial market. 1 was a cylindrical pre-filter intake tube configuration based directly on Briggs's original channeling design principle from 1964. The results were published in the SAE International Journal of Engines in 1984. Intake-modified engines showed a 44% reduction in cylinder wall wear particles recovered from oil samples after 10,000 miles of standardized driving cycles. Combustion efficiency increased by 31% compared to factory configuration baselines across all tested units. Projected engine lifespan based on measured wear rate data extended to an average of 287,000 miles versus 118,000 miles for factory specification equivalents running under identical conditions. The study was peer-reviewed. The methodology was sound. The data was independently reproducible, and no American automotive manufacturer responded to the published findings publicly or privately in any documented record that has ever been located. The auto industry did not hold a meeting and vote to suppress this. It did not need to. The suppression happened automatically through a system already perfectly designed to ignore anything that threatened its revenue model from any direction. Dealership service training programs never included intake optimization as a subject. Mechanic certification curricula controlled by the National Institute for Automotive Service Excellence never mentioned combustion airflow efficiency as something a consumer could address independently. Oil change chains trained every customer-facing employee to recommend factory air filter replacement on the manufacturer's schedule every single time without a single exception or alternative mentioned. Auto parts retailers built entire wall sections around name-brand filter replacement products that solved nothing beyond what the factory intake system already provided at a lower cost. The automotive press, funded almost entirely by manufacturer advertising budgets, never once ran a feature explaining why the factory intake system is the single most under-engineered component sitting under your hood right now. You were never supposed to know that a section of Schedule 40 PVC pipe from the plumbing aisle at any Home Depot or Lowe's in the country, cut to the right length, connected to your factory airbox inlet with a universal cone filter, could fundamentally change how long your engine survives. Not someday. Starting with your very next drive, here is exactly what to do starting today. Go to the plumbing section of any Home Depot, Lowe's, or local hardware store near you. You are looking for a standard 3-inch diameter Schedule 40 PVC pipe. By 124-inch length, it costs between $280 and $340 depending on your location. You will also need a universal cone air filter. The two that perform best in independent testing are the K&N RC1780 and the Spectre Performance HPR96111. Both are available on Amazon, at AutoZone, and at O'Reilly Auto Parts locations nationwide for between $7 and $12. You will also need a standard hose clamp, available at the same hardware store for under $2. Cut the PVC pipe to 12 inches using any standard hacksaw. Sand the cut end smooth so there are no rough edges that could affect airflow. Open your hood and remove your factory airbox cover. Disconnect the factory inlet snorkel, the tube that feeds air into your airbox from the front of the engine bay. Fit the PVC pipe directly into the airbox inlet port. Most 4-cylinder and V6 applications accept a standard 3-inch diameter pipe with no additional adapter required. Secure it firmly with your hose clamp. Attach the cone filter to the open end of the PVC pipe using the clamp that comes included with the filter. Reinstall your airbox cover. Start the engine and simply listen. The intake note will change immediately. Deeper, smoother, more consistent through the entire RPM range. That sound is your engine breathing correctly, possibly for the very first time since it left the factory floor. One honest note before you move on from this video. This modification works best on engines with under 150,000 miles that are already mechanically sound inside. If your engine has significant existing blow-by or measurable compression loss, improved airflow alone will not reverse damage that is already done structurally. The real power of this is entirely in early application. An engine that breathes correctly from 30,000 miles will simply outlast one that does not under any driving conditions at any mileage level. That is not a promise. That is 60 years of documented engineering data from military records, NASA maintenance logs, and peer-reviewed science that the industry spent decades making sure never reached your driveway. This information never disappeared. It was never lost. It sat in military maintenance logs, NASA ground crew records, and peer-reviewed engineering journals for 60 years, waiting for someone to look past the $110 billion wall that was built around it. Your engine is wearing down right now as you finish watching this. The PVC pipe costs $3. The cone filter costs $8. The hose clamp costs $2. The knowledge costs nothing at all. What costs everything is never knowing any of this existed. If this opens something for you today, subscribe and share it right now with someone whose engine deserves to survive well past 100,000 miles. Because the industry spent 60 years making absolutely certain they would never find this on their own,